Okay, here we go. Last section of chapter 13. Okay, Le Chatelier's principle, and you should have a good feeling for this section. It's something that students tend to like. It's all logic, very much if, then, and therefores. So here's what Le Chatelier's principle states. If a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. So if I put a stress on the system shifts the equilibrium to reduce the stress. So what can change the equilibrium position? Concentration. If you add an aqueous or gaseous substance that appears in the reaction, then the reaction will react to get rid of that substance. If you add a substance that reacts with something that's in the reaction is going to make more of the substance that reacted. Now, if you add more of a solid or liquid present in a reaction, it has no effect on equilibrium at all. No effect. However, if you add something that's a gas or aqueous, then you can actually change the mass of a solid or liquid, but adding the solid or liquid doesn't change anything else. It's important. It's an important difference here. We can change the mass of the solid or liquid, but adding the solid or liquid doesn't change the amount of gas or aqueous substance. Very important here. If we change the concentration, there's no effect on K, none whatsoever. No effect on K. It affects Q, the reaction quotient. Remember, those are initial conditions. All right? And by changing Q, the reaction has to respond by getting back to K, but we don't change K. All right, moving forward. Pressure. Changing pressure. Well, if you add reactants or products, changing pressure is like changing concentration because you're adding more of a reactant or a product. However, if you add an inert gas, that's a gas that's not a reactant or a product and doesn't react with a reactant or product, and there's no effect on the equilibrium position. If you change the volume of a container, then you do have an impact. Increasing the volume of the reaction vessel, sometimes it's called a vessel, that causes the equilibrium to shift to the side with more moles of gas. And the reason is, if you increase the volume, it means you have decreased all of the pressures of all of the gases. So if you decrease the pressure of all the gases, you need to create more gas. So you go to the side with more moles of gas because you need to create more gas if you've decreased the concentrations or pressures of all the gases. Okay, if you decrease the volume of the reaction, that means all the concentrations are increased. All the pressures have increased if you decrease volume. Remember, pressure and volume are inversely related. So if we increased the pressures of everything, we need to ultimately decrease the pressure, the total overall pressure. So we go to the side with fewer moles of gas. Changing pressure does not affect K, it only affects Q. And then the reaction reacts to get back to K. Last thing, temperature. If we change temperature, we have to think about whether the reaction is endo or exothermic, and whether heat is a reactant or product. So we use the endothermic, exothermic information to see whether we put heat on the reactant or product side. When you heat a reaction, we have to remove heat. So it depends if the reaction is exo or endothermic. You just have to make sure if you increase temperature or heat a reaction, we move in such a way that we remove heat. If you decrease temperature or stick a reaction container on ice, the reaction wants to create more heat, so it'll shift to the side where the heat is. And very important, if we change temperature, we have affected K. K changes. That's because we did not change Q, but the reaction does shift. Well, if the reaction shifts and we didn't change Q, we sure better have changed K. So in thinking about whether K goes up or down, it depends on whether we create more products or more reactants. If we make more products, if we shift to the right, K goes up. If we shift to the reactants, shifting to the left, I'm trying to underline reactants over there. If we go left, then K decreases because reactants are in the denominator of the equation for K. So let's do some Le Chatelier problems. When you're doing a Le Chatelier problem, you have to explain your reasonings for any conclusions that you make. And you need to be specific about what change will occur and why. Instead of discussing Le Chatelier, you can also discuss Q versus K. If Q went up, based on the changes that occurred, products are too big, so you have to shift left. If Q went down, based on whatever change you did, then products are too small, and we need to shift right, because we always have to get back to K, the equilibrium constant. Okay, I've taken some old AP chemistry problems, starting with the 1998 problem. Here's our reaction. Notice we have a solid here. So we have to think about the rules for solids, and we have two gases. And this reaction is endothermic because we have a positive delta H. All right, here's some background information. Oh, and it's important to note that some solid remains in the container at equilibrium. That's just telling you the system is at equilibrium and there's some solid sitting there. Okay. First question, what is the effect on the equilibrium partial pressure of ammonia gas when you add more solid NH4HS? Think about it for a minute. I'm about to put up the answer, so pause if you want to think about this on your own. And I'm going to talk a little bit. Pause while I'm talking if you want to answer this on your own. So we're adding some solid, and you want to think about what do solids do? Well, solids don't do anything. No effect. Solids don't do anything. Okay, that was easy. Another question, same reaction. These are all the same reaction. So what's the effect on the equilibrium partial pressure of ammonia gas when you add H2S gas? Okay, so go ahead, pause if you want to. I'm going to talk us through this. So we're adding some H2S. The system wants to get rid of the H2S, so it's going to shift left. When it shifts left, it's going to make the ammonia go down. There you go. By Le Chatelier, adding H2S causes the system to remove H2S, making the equilibrium shift left, causing the partial pressure of NH3 to decrease. This one is tricky. What happens to the mass of NH4HS when we decrease the volume of the container? You have to really think about this one. So pause if you want to. I'm about to go through this. So we decrease the volume. That means that both the pressure of ammonia and H2S increased. So the pressure of both of these increased, which means Q is too big. We were at equilibrium. We were at K. Now I've made the products go up. I didn't change anything about the reactants. So Q is too big. I got to get back to K. I got to get rid of some of the products. The reaction is going to go to the left. And that will make not the concentration, but it'll make the mass of NH4HS go up. There you go. There's your answer. You can pause and write that down. All right, new question. Pause if you want to think about this on your own. Okay, we're going to increase the temperature. We want to think about what happens to the mass of solid NH4HS. Well, we made temperature go up. This reaction is endothermic, therefore heat. I cannot write with this. Heat is a reactant. That's me writing heat on my keyboard. Okay, so heat's a reactant because we have an endothermic reaction. I increased temperature, T goes up, so I want to get rid of heat. In order to get rid of heat, I'm going to move to the right. And if I move to the right, that means the mass of NH4HS went down. Here's your answer. Don't pause yet. I want to talk a little bit about what happened to K. That's not in the question here. But if I increase temperature, that makes the reaction go to the right. I had not changed Q. So my equilibrium constant, if I go to the right without changing anything else, I'm hopeful that you see that K would increase because I increased the partial pressures, and K is partial pressure of NH3 times partial pressure of H2S, KP is, and that would make KP go up. New question. This is another AP question from 1977, and these are all in the equilibrium file that we have for class. Okay, so here's our reaction. Notice everything is a gas. Oh, we also know that delta H is negative, which means heat is a product. We're going to put heat over here on the product side. Okay, we're at equilibrium, and we want to predict how each of these changes affects the equilibrium constant and on moles of SO3 at equilibrium. And we have to explain. All right, decreasing the volume of the system. Pause if you want to do this on your own. And I'll go through the explanation. If we decrease the volume of the system, that means we increased all the pressures. P goes up. We increased all the partial pressures. Notice this side has more moles of gas. So the reactants went up more than the products did. The products only went up a little bit compared to the reactants, which means Q, we increased the reactants more than the products. So Q is products over reactants, which means Q is smaller than K. So I gotta make more products so I can get back to K. Let's see what's written here. Okay, there's a big long explanation. Go ahead and read it. So we go to the right in order to get back to K. So if we go to the right, SO3 goes up. The moles of SO3 goes up. Not necessarily the partial pressure, but the moles of SO3 go up. And there is no effect on K because all we did was we made Q, let's see, the reactants went up, Q was too small, and we went back to K, but we didn't change K, we just went back to K. All right, this time we are going to add oxygen to the system. And we want to know, how does this affect K, and how does it affect SO3? Pause if you want to answer this on your own. Here we go. If I add oxygen by Le Chatelier's principle, we want to we got to make the oxygen go down. In order to do that, we got to go to the right. And if we go to the right, SO3 is going to increase. So you'd write that all down. Moles of SO3 will increase. As far as K is concerned, I don't affect K at all because I added oxygen. I didn't change the temperature. The only thing that affects K is temperature. Here you go. Here's the written response. Oh, we've changed temperature. We're going to affect K this time. All right, let's see, delta H is negative, so heat is a product. And I increase temperature. Pause if you want to do this on your own. I increase temperature, so the system wants to get rid of the heat. The system's going to go to the left. Going to the left is going to make SO3 go down. And the products went down, reactants went up. That will make K decrease, because K is products over reactants. And here's all of those words I just said printed out. If you want to read that, you can read that. Okay. Big note here, very important. Highlight. The only thing that affects K, is temperature. Make sure you make a big note of that. So any other changes have no effect on the equilibrium constant K. Your turn. I'm not going to go through all the answers on these. I'm just going to put it all up, and you will get to write down what's going on. But I will give you a quick explanation of what's happening here. So this cobalt complex right here is pink. And over here, this cobalt complex is blue. Notice the blue test tube over here and the pink test tube over here. And when you are somewhere in the middle, a mix of both complexes, you're purple. Okay, so this over here in the middle is purple. So if we go to the left, we'll turn more pink. To the right, we'll turn more blue. And somewhere in the middle, you're purple, because pink and blue makes purple. Okay, so for the reaction above, you're going to predict the color the solution will turn, either pink or blue, meaning you went left or right, when we put each of the following stresses on the system. So we would take one of these purple test tubes and do something to them. And we got to determine, is the reaction going to go to the right or the left, and thus turn pink or blue. Okay, so you should have this all printed out, unless your printer wasn't working. So you're going to have to pause. These are the 4 questions. Okay, make sure you get all those 4 questions written down, or hopefully you have them down already. And then you're going to answer whether you'll turn pink or blue and explain why. And there is a 4-minute video which shows this reaction and what happens. So you can actually see the pink and the blue appearing from the purple and see if your predictions were correct. So this is how you will check your answers and see if you predicted it correctly.